Hey there, awesome physics students. I want to do another circuit analysis example to show you how to analyze series and parallel combination circuits, and especially how to think about them to connect back to what we know about how current and voltage behave in circuits, which is the most important thing we want to get from this. So here's our circuit. We have a 4.2 volt battery with resistor 1 at 5 ohms, resistor 2 at 3 ohms, and resistor 3 at 6 ohms. First of all, what we want to get from this is just everything. We want to get the total current. We want to get the current through each resistor and the voltage drop across each resistor. So we want to know everything about this circuit. The first thing you want to do when you look at this circuit is you want to recognize which components are in parallel and which are in series, and can you identify any of these things right away based on your knowledge of how current and voltage behave in circuits. Well, it may appear that these all are in parallel with each other, but that's not true when you think about it a little more carefully. Imagine you're a charge, you come out of the battery, you have to go through R1. You have no choice. On the other hand, when you come here to this junction, you can choose to go through R2 or R3. So there's a split there. That tells you that R2 and R3 are in parallel with each other. And because everyone has to go through R1, R1 is in series with the whole thing, the combination of R2 and R3. Another way to see this is to just drag, you're allowed to drag these things around and pull them and morph this circuit how you like, as long as you don't make or break any new connections. You could redraw this like this. So it comes out of the battery, it goes through R1. So here's R1. And then it splits into, as it comes here, it splits either R2 or R3. So it splits R2 or R3. And then it joins back up here. That's here. And then it goes back into the battery. Okay, so this is equivalent. These are the same circuit here. Okay, so to first think about this, let's get the total current here. To get the total current, I want to get the total resistance or the equivalent resistance for this whole thing here. So I want to first smush the R2 and R3 into one resistor to get R2, 3 equivalent. And because these are in parallel with each other, I need to use the parallel formula. The parallel formula says 1 over R1 or R2 plus 1 over R3. It will give me the 1 over the total. But I need to invert that to get the total. So don't forget about this inversion at the end here. So this is going to be, this is 3 and 6 ohms. So this is 1 over 3 ohms plus 1 over 6 ohms. And I have to invert that at the end. When I do all this math here, I'll let you do that on your own. I get 2 ohms. So this equivalent here is 2 ohms. Okay, this one is 5 ohms, so the total resistance is going to be this 5 ohms plus this 2 ohms. So that's going to be 7 ohms total. Well, now let's go back to this I total. I can get I total by using delta V total over R total. The total resistance is 7. The total voltage from the battery, that's 4.2. That's going to be 4.2 volts over 7 ohms. And so when I divide that, I get 0.6 amps, or 600 milliamps. If you were measuring it on a voltmeter, you would see it as 600 milliamps. Okay, so I can go ahead and fill this in. This is 0.6 amps. All right, so now let me look at this. Now that I have something on the board here for this, let me think about what this means. All of the current that comes out of the battery, that's 0.6 amps, all of that goes through R1. So the current through R1 is all of the current. So I1 is 0.6 amps as well. And I can just fill that without doing any calculations. I just know that comes from knowing how current works. Current is flow. All of the flow that comes out of the battery has to all go through R1. And then it comes out and then it can split. So some of that 0.6 comes through R2 and some of it comes through R3. Now to get how much comes through R2 and R3, let's put that off and let's go to some of these voltage drops here. I can also look at the voltage drop across R1, delta V1, and that's just going to be the current through 1, which I know is 0.6 amps, times the resistance of R1, which I know is 5 ohms. So that's going to be 0.6 amps times 5 ohms. And when I multiply that out, that gives me 5 times, that's 3 volts. So that tells me that the voltage drop across this, I start at 4.2 volts, and then I reduce that by 3 going across here. So the voltage drop for this first resistor is 3 volts. Okay. Now, knowing how voltage and current work here makes it so much easier. If I've dropped it, if I started at 4.2 volts relative to 0 on the negative terminal of the battery, it's 4.2 here, it reduces by 3 there. So that means what I have left over is 4.2 minus 3. So I could get this delta V2. If I look at delta V2 and V3, those have to be the same. Now, how do I know that they're the same? Well, if I measure the voltage drop across R2 by putting the probes here of my voltmeter, I could move it along here without lifting it, and that would be the same as R3. So the voltage drop across R2 and R3 have to be equal to each other. And furthermore, I know that if 3 of it drops across the first one, I only have 1.2 left, right? That's going to be 4.2 volts minus 3 volts. That's what's left over. And so that's going to be 1.2 volts. So I have 1.2 volts for each of these. Now, there's another way to do this. I could say, well, the equivalent resistance here is 2 ohms. And these are the same, of course, I need to know that. So the equivalent resistance there is 2 ohms. And the current, the total current that goes through here is 0.6. So this is be 0.6 amps times the total resistance, which is 2 ohms for that branch. 2 times 0.6 is 1.2 volts. Well, that gives me the same thing, okay? So usually there are a couple ways to get this, but they had better be consistent, and if they are not, you have done something wrong. All right, so I've got most of these. Now I need to know what the current through I2 and I3 are. Because I know the voltage drop across I2 and I3, I can get that. So the way to do that is I2 is going to be delta V2 over R2. R2 is going to be 3 ohms, and the voltage drop is 1.2 volts. So 1.2 divided by 3 is going to give me 0.4 amps. So I2 is 0.4 amps. Now, one way to get I3 is to note that if I have 0.6 coming through here, that's the total current, and 0.4 of that goes through here, that means I have left over 0.2 going through here. So this has to be 0.2 amps. I can check that though. I can say, okay, that's got to be equal to delta V across 3, which is 1.2 volts, divided by resistor 2, or excuse me, resistor 3, which is 6 ohms, tripping here. So this is 1.2 volts, that's the voltage drop across 3, divided by the resistance of 3, that's 6 ohms. 1.2 divided by 6 is 0.2 amps, exactly what we had thought it should be based on whatever current was left over. So you notice that there's a great deal of consistency in this approach, and all of these things, if you do it 2 different ways, you get the same answer. Oftentimes it's better to get the answer that you know based on how current works and how voltage works. But key, that makes the whole thing much easier. I do have to do some equivalent resistances here, which is fairly straightforward computation, but the rest of it I really need to think about, all right?